for platform-based mechatronic design. Now, since our time is quite limited, well, this is just the contents of my presentation. I will start a brief introduction about the subject with an overview of modular design research, and then I'll try to explain my objectives, scope, and methodology in this work. And I will mention about mechatronic behavior modules and their conceptual structuring, and then how can we represent mechatronic systems using, in general, using these mechatronic behavioral modules using a new approach, which is 3D design structure matrix representation, and very, let's say, laboratory level case study will be shown, and conclusions in future work will be the last parts. Now, today's technological developments and changing customer requirements have shifted, companies to move from their mass production paradigm towards mass customization paradigm, basically. So that paradigm means that you have to, as a company, you have to develop a certain product family with different tasks, and you have to adapt to changing customer needs. Therefore, this type of product development together with manufacturing facilities would require platform-based products, basically, which means that we have a common platform and we have a variety of modules which are connected in such a way that we can produce different types of products within a certain range, of course, quickly and easily. So what people need in that respect, we need systematic methods for this type of modularization and platform-based product family design, and there is considerable amount of research in this area, especially in the last decade. Well, just to name a few of them, of course there are more than these, very valuable research to construct systematic methods for such product design strategies. But what we have noticed was that these methodologies are basically for mechanical products. Plus, there is another thing, that they are mainly component-dependent methods. So they suppose that you know the system physically, you have the system, so you have the physical components in the system, how you can relate the physical components, then do this with some clustering, very valuable clustering methods. You cluster the physical components into modules, and then by rearranging the modules, you can produce new products. So what I have noticed as a missing part, the gap, we need a research for the modular design of mechatronic products at the very early stage of engineering design process, in which you don't have the system anymore. You have the system in your mind only. So this is the starting point, and therefore with the starting point, my objective was the development of an initial conceptual scheme for systematic design of platform-based mechatronic product families for mass customization based on an event-driven operational behavior, which is our previous work, in fact. So the methodology that we have used is that we are using state-based representation of the operational behavior of a mechatronic system at a very early design stage, and for this purpose we have used discrete event system specification model by Ziegler. That was our previous research, and we published this research already. And then using that, now what we have in this study, in the current study, using that best model, conceptual structuring of behavioral modules can be constructed. And then representation of mechatronic product family, which I call it as a robot family short, via a three-dimensional design structure matrix using these very abstract behavioral modules. And then just to have an implementation with a very limited budget in this work, theoretical design and implementation. So my concern is basically the development of the theoretical part, and then of course we need always the implementations, so I will mention about that one. Now, mechatronic behavior models are using behavioral design approach, and well, this is an event-driven model that we have developed. So it dates back to 1989 by Ziegler's methodology. Let me just show this figure, which explains the whole story. The model is based on a very general mechatronic system. So this is your mechatronic system with the system boundary. Here, as you see, now in a mechatronic system, we have 3 steps in any mechatronic system: perception, cognition, and motor action. And the operational behavior of a mechatronic system can be accomplished via the state changes. And these state changes are determined by using some input and output events which come from the underlying field. So this system is connected, there are double-sided connections with this system and the environment outside the system, which first of all, if there's a change in an environment, then well, this change is perceived, and then with some cognition, reasoning, and decision-making, some motoric actions are produced, and as a result of these motoric actions, that means some task execution, the system changes the environment, which appears as an output event. So you can access this. This is our publication over there. If you are interested in the model, you can just access this publication. So I skip a few slides. Based on this model, we developed the theoretical structure for the behavioral models. Because of time limitation, I skip all this because the whole story is here. Now, this is the extension now for this current research. Now, still we have our system. We don't have the system, we know only what to do with the system. So what is the behavior of the system? What the robot will do, in other words. So we have the perception modules, we have cognition modules, and we have motoric action modules. And the structure is as before. But what is interesting here is the following. We have several changes in the environment. There may be an obstacle, there may be a change in the temperature, there may be a sudden noise, etc., etc. So what the system should perceive in the environment are represented here. So this is, let's say, W number of changes in the environment. And then each one is detected and processed by the perception behavior module. Now, cognition modules are considered as basically what we call software modules, and these modules develop the reasoning and decision making. Therefore, corresponding motoric actions could be decided. So, if you come to the motoric action state, let's say, we have motoric action modules, and these modules are arranged in an array. Why? Because each motoric action, let's say, row in motoric action array represents a set of motoric actions that the underlying robot, that is the robot in one of the robots in the product family, will exhibit this type of motoric actions as a certain sequence. And these motoric actions will result in changes in the environment, depending on what type of behavior you would like to obtain. So this is the conceptual structure, and then the next question appears. Okay, we will have, let's say, n number of robots in the product family, and how can we decide on the modules and their interrelationships between these products? So let me just show you the representation first of all, which is inspired from the two-dimensional design structure matrix. But what is different here is that we have a three-dimensional case. Why? mechatronic system, we have perception, cognition, and motoric action. Therefore, in each these modules are placed as mutually perpendicular in this structure. Now, what these geometric shapes show, there are the different robots in our family. Now, I have the same colors, same shapes in the example, so I will refer to this figure back. But, for example, if you have 3 different robots, this is just an example representation. You have 3 robots. Let's say if you have a relationship between cognition model C1, perception model P1, and motoric action model L1, then this type of relationship exists in all 3 robots. However, for example, if you have C8 and the corresponding M5, I think, if I'm not wrong, and P1 again, then this type of relationship exists only the green robot that you have. So this is the main story, and then let me by referring back to this figure, let me explain our small case study as an implementation. So this is just an implementation on a demonstrative task-based mechatronic product family model, just a small model, in the laboratory. So we have considered assistant or service robots and behavioral design of a model robot family with 7 robots have been studied. 2 guide robots for museums and shopping malls, 1 guide robot, 1 home cleaning robot, and 3 companion robots for children, the elderly, and the pets. So we considered only simple robot tasks because, well, this study, there were some undergraduate students helping the study, no other graduate students, nobody else. Therefore, very simple robot tasks has been considered. Well, these are the examples, which I have the same, figures on the 3D design structure matrix representation. So you can represent 3 robots: museum guide robot, guard robot, and company robot for the elderly. So you can construct some relationships as an example table. For example, these relationships, if there's an obstacle, these are the perception modules, cognition modules, cognitive modules, and motoric action modules. Now, for example, if you have an obstacle, you can represent as an obstacle detection is needed, or you may need a tactile perception, or you may need a sound perception in certain cases, depending on the task of the robot. And then, for example, sometimes you may need, if you detect an obstacle by the related software, by this way, there's no explanation for the software modules, because those software modules depends on what you will do, what is the relationship with B. So sometimes if you have an obstacle in front of the robot, you would like to stop, but sometimes then you may just turn right or left. So the motoric action behavior may also change, and which robots have these relationships, you can just determine all these. But this determination for the time being is manual, that is, it depends on the designer's intent. However, what is the purpose? Of course, doing this in a systematic and formal way. What we have done in the rest of this study, by using these relationships, we try to symbolically structure the physical representation of these modules, at least, with the available items that we have in the laboratory. And then we have constructed the design of those physical models, and just for representing the real physical robot model. So with different modules, simple tasks can be accomplished. So this is the main platform, and modules are changing in this study. So now, as conclusions, this is modular design methodology of mechatronic products at early design stages. The scheme is component independent. It only depends on the behavior of the robot that you would like to design. So that we call it as behavioral modules for perception, cognition, and motoric action. So it is using a 3D design structure matrix representation, which is a modified form of existing design structure matrix. That is a very useful method for analysis clustering. So we are trying to represent the mutual interactions between these modules. And we are working on this subject still. So relationships between behavioral elements in this three-dimensional design structure matrix instead of physical components, since no physical system exists at this stage. This is quite important. And, well, one difference between the design structure matrix and what is our approach. All these groups are different. I mean, in a design structure matrix. In each dimension, we have different types of, let's say, behavioral items, not the same items, because if you know probably the design structure matrix, you have the same items, and you have the physical relationships, therefore you know how to connect these items. But the problem here is that we have different types of items, and we have to develop formal representation, formal methodology to relate all these items, three types of items together. So these parts are the main contributions. And now future research, in fact, we are still working on this. We started. So we need the development of a formal structure to describe those behavioral modules for mechatronic products, formal structure, and formal representation, and also analysis and clustering of the behavioral modules using this 3D DSM approach. So how can we cluster them in general without any physical implementation, first of all, and then apply and implement this formal structure representation into both conceptual and physical structure, physical implementation, and put it as a complete formal model. So we are still working on these, so we are trying to get support. I hope so, because we have, well, such work is not mainly supported by industry in Turkey. We have some limitations about that, but still we are trying to find some support, and I hope we can do this. Okay, thank you very much for your interest, and if you have time, if you have any questions, I will be happy to answer.
Thank you very much.